Hello, hello, hello. In this episode of What's the Big Idea, we're going to continue to talk about these fundamental quantities that describe rotational motion, angular momentum, and torque. But whereas previously we only considered situations in which the objects that were rotating had an axis of rotation that was fixed in its direction in space, we're now going to relax that constraint. And what we're going to find is that we're going to have to consider both angular momentum and torque to be vector quantities. So we're really leaving a sort of one-dimensional world and branching out into a broader three-dimensional world. And in that three-dimensional world, we're going to discover exciting and new and important phenomena such as precession. So let's dig in. So we'll start by reminding you of the existing state of affairs when we did have a fixed axis of rotation. And as our canonical object, we'll continue to take a bike wheel and imagine that this dotted line represents the axis about which the bike wheel can rotate. And if we constrain ourselves so that the direction of that axis doesn't change, then we've shown that there is an angular momentum associated with that spinning bike wheel. And the angular momentum points in a direction perpendicular to the plane of the bike wheel. And since the angular momentum has to be perpendicular to the plane of the wheel, there are really only two choices for which direction the angular momentum of the wheel can point in. It can either point to the left here, the way it's shown in the figure, or it could point in the opposite direction to the right. And the way we distinguish between those two choices is to use a right-hand rule. So you this version of the right-hand rule says that if you curl your fingers with the rotational motion, the fingers of your right hand, then your thumb will point in the direction of the angular momentum. If the wheel were to spin the other way and you applied the same right-hand rule, you should convince yourself that you would predict that the angular momentum is pointing in the opposite direction. And not only that, but we're able to write the angular momentum as the product of the rotational inertia of the object times the angular velocity of the object. So that means angular velocity also has a direction associated with it. It points along the axis. In the example shown here, the angular velocity points to the left in the same direction as the angular momentum. If you reverse the direction in which the wheel was spinning, both omega and the angular momentum would change direction and point to the right. So it'll still be true that L is equal to I times omega. And then we also wrote down a version of Newton's second law for rotational motion in terms of the angular momentum and the torque. So this version says that if you want to change the angular momentum of the spinning wheel, you have to exert a torque on the wheel for a certain amount of time. And from this relationship, it follows that the torque also is going to have a direction which points along this axis. It's either going to point to the left or the right. And to see that, just imagine that the wheel was initially at rest, so that initially the angular momentum was zero, and you wanted to get it spinning the way is shown in the figure, so that LF points to the left, the way it is shown here. So if you start with zero angular momentum, then the change in angular momentum is just equal to the final angular momentum. So if you start with the wheel at rest and you end up with the angular momentum pointing to the left, it must mean from this relationship that you exerted a torque which points to the left. And similarly, if the wheel started from rest and you wanted it to spin in the other sense, you'd have to exert a torque pointing to the right along the axis. So in this constrained world, constrained by the fixed direction of the axis of rotation, torques can really only serve to speed up or slow down the rate at which the wheel is spinning. Those are the only two choices in town. It's pretty much exactly analogous to when an object is constrained to move in a straight line with linear momentum. And if we write down the second law for the case of an object moving in a straight line, the forces that are exerted on an object with momentum can either serve to increase the magnitude of the momentum or decrease the magnitude of the momentum. That is, they can either forces can only serve to speed things up or slow things down. Those are the only two choices in town. Now, if you recall what happened when we went from one-dimensional motion to motion in two or three dimensions, the way Newton's second law gets modified is that we have to treat the linear momentum and the force as vector quantities. And so the Newton's second law in two or more dimensions gets written this way, just with little arrows over the quantities. And we're now representing momentum as a vector and force as a vector. And this opens up new possibilities, because now you can have an object with momentum in one direction and you apply a force in another direction. And the effect of the force may not be to speed the object up or slow it down. It may be to change its direction. So a familiar example of uniform circular motion is if you always exert a force perpendicular to the momentum, you cause objects to go in a circle. So if we're going to modify our version of Newton's second law for rotating objects to allow for things to happen in a three-dimensional world, both the angular momentum and the torque are going to have to be considered to be vector quantities. So we're going to write the second law by putting arrows over both the angular momentum and the torque. And now we want to consider a situation. Suppose you have a bike wheel that's spinning in the direction shown so that its angular momentum points to the left, as is shown. Imagine that somehow you manage to exert a torque that points in a direction shown here, so perpendicular to L. Well, what do you expect to happen? It's very much analogous to what happens in the case where you exert a force perpendicular to a linear momentum. You expect the effect to be to change the direction of the angular momentum, but not its magnitude, just the same way that in this case, a force directed perpendicular to a linear momentum doesn't change the linear momentum or the speed of the object, it just changes its direction. Well, how do we exert a torque in that direction? Well, a torque in this direction would be a torque which caused an object which was at rest to rotate around an axis that points in that direction. So a torque, to get a torque in this direction, you just have to apply forces of some sort that would cause this wheel to rotate about an axis which is drawn in this direction. Well, how can we do that? Well, it's easy. Suppose we just imagine suspending this. Imagine there's a handle on this bike wheel and we just suspend the bike wheel from a string. Then gravity is going to exert a torque in exactly the direction that I've shown here. And we would expect to see a situation in which the direction of the angular momentum of the spinning bike wheel changes, but not the magnitude of the angular momentum. So let's see that happening with the following video, which comes again courtesy of our good friends at the MIT physics department.
Suppose I have here a string, a rope, like we have there. And I stick into that rope, I attach to the rope this wheel, just like so. And I let it go. Well, we all know it will happen. Clunk. It's clear. All right. But now I'm going to spin it before I let it go. Where's the wheel? The wheel is here. So we'll spin it up, and then we'll put it in here. Notice the way I'm spinning it. I'm holding it away from you now. I'm going to change it and do it differently next. And there it goes. About 10 seconds. Isn't that amazing?
Yes, that is certainly amazing. That phenomenon is known as precession. And precession is an important phenomenon. It's really the phenomenon, for example, that underlies magnetic resonance. So when you go in for an MRI, magnetic resonance imaging, the nuclei of the water molecules in your body have an angular momentum, and you are put into a big magnetic field, and it turns out that the signal that is generated in an MRI is due to the precession of the angular momentum of the nuclei of the water molecules in your body. And that is the basis of how we get these wonderful images. So understanding precession, this phenomena of what happens when you apply, when you have an object with angular momentum and you apply a torque perpendicular to that angular momentum, that's a really both counterintuitive and also important phenomena in the world. Let's talk about one more aspect of this problem, which is interesting. So I'm going to start by rewriting our rotational version of Newton's second law in vector form. And the thing we want to focus on here is what determines how quickly the precession takes place. From our fundamental relationship here, we see that the uh, the change in angular momentum that occurs during a certain time interval will be proportional to the torque that is applied. So if you have a bigger torque in a given time interval, you would expect a greater change in angular momentum. And in this situation where we're applying a torque perpendicular to L, that torque is only causing the direction of the angular momentum to change, not its magnitude. With a greater torque, if we somehow manage to increase the torque in a given time interval, we would expect the direction to change more, and that must mean that the precessional rate will be faster. The direction in which it's pointing in will change more if the torque is greater.
So we let it first go around, which was roughly 10 seconds, what we calculated. And now I'm going to put 2 kilograms here at the end. And then you will see an instantaneous increase in the precession frequency. You see, it goes much faster now. I take it off, and then it goes back to its roughly 10.
So now we want to get a little bit more fundamental and mathematically quantitative in our description of how the vector nature of things like angular momentum and torque. So what I want to talk about is let's consider that, still consider our spinning bike wheel, but now let's recognize that any object in the world is made of a collection of particles. And just like when we had a system consisting of particles with individual momenta and we wanted to get the total momentum of the system, we just added up all the individual momenta to get the total momentum of the system. The same thing should be true for our bike wheel. But this angular momentum of the bike wheel that we have, which we've argued points in the upward direction, we should be able to break the bike wheel up into little particles and describe what the contribution of each particle is going to have in angular momentum. And the way we're going to get this total angular momentum is to sum up all those individual contributions. So what I'd like to do is I'd like to consider one particular little tiny particle that makes up our bike wheel, indicated by this little green dot. And at the instant in time which I'm showing, the little green dot has a position vector r measured. We're going to choose as the origin of our coordinate system, the center of the bike wheel. And this blue arrow here represents the position of our little mass, our little particle at the particular time shown. And then at this instant shown, the linear momentum of that green dot will be in the direction of the red arrow. And now I'm going to essentially define the angular momentum of that particle as in the following way. I'm going to introduce a new mathematical concept called the cross product. It's a way of cross product is a way of multiplying two vectors. And we're going to define the angular momentum of this particular green dot as the cross product of the vector r and the vector p. So what is a cross product? So this figure down here shows you how we define the cross product of any two vectors. So imagine I've got a vector A, the blue arrow, and a vector B, the red arrow, and these two arrows are separated by some angle, which we'll call phi. Then the cross product of A and B, and the order of these in which we write the cross product matters, as you'll see. But A cross B is defined as a new vector that lies perpendicular to the plane, the plane that contains the vectors A and B. So that we've tried to draw that here. A cross B is perpendicular to both the vector B and the vector A. And not only that, but the rule for determining the magnitude of the cross product of two vectors is you just take the product of the magnitudes of the individual vectors, and then you multiply by the sine of the angle between the vectors. So that means, for example, that if A and B are perpendicular to one another, then the magnitude of the cross product of A and B is just the product of the magnitudes of vectors A and B, since the sine of 90 degrees is 1. And so there's a last bit of trickiness. We can say what the magnitude of the cross products of two vectors is very easily, and we say the direction is perpendicular to the plane uh, containing the two vectors, but then that leaves two choices. Does it point in the direction shown here, or it could be in the opposite direction and still be perpendicular to that plane? And the way you distinguish between those two possibilities is with a version of the right-hand rule. So here's a popular version of the right-hand rule. You take your right hand, that's the first important thing, and you have a thumb, and then the next finger in, you point along the direction of the first of the vectors, A in this case, and the second finger after the thumb, you point in the direction of B. And if you can orient your fingers so that these two fingers point along A and B, then your thumb will point in the direction of A cross B. And that's what's shown here. If the thumb is aligned parallel to vector A, and I'm sorry, if the first finger is aligned parallel to A and the second finger is more or less parallel to B, then your thumb will point in the direction of A cross B. So what all that says is that if we go back to our description of the angular momentum of a particle on the rim of a bike wheel, R points this way, P points this way, you should convince yourself that if you take R cross P, you have to be, first of all, in the plane perpendicular to the plane that contains R and P. So you've got to be along this axis. And then if you apply the right-hand rule, you should convince yourself that it indeed points upward along that axis. And that's good news, because if you go along and you consider all the points that make up the bike wheel, each one of those points is going to contribute an angular momentum that points upward along the bike wheel. And so when you sum them all up to get the angular momentum of the entire spinning bike wheel, you're going to get an angular momentum that points up as shown. And if you were to reverse the direction of the spinning wheel, you should convince yourself that in that case, the angular momentum of each of the particles points down, and therefore the angular momentum of the entire spinning bike wheel points down. Well, in a similar vein, we'd like to give a mathematical and more precise definition of the way to compute torques. When you know that in order to exert a torque, you have to, about a certain axis, you exert a force, and that force has to be exerted at a particular place. It's applied at a particular place, and we're going to measure the torque around the axis that points through the center of the bicycle wheel. So the proposed way to calculate the torque is in terms of a cross product of this vector r and the force vector F. So the blue arrow is the vector R, and the red arrow is the vector F. And if we if we use our right-hand rule to calculate the direction of the torque, if we take R cross F, we're going to get a vector that points in the direction of this brown arrow here. And that makes sense because if you think about it, if this wheel were at rest and you came and you exerted a force in the direction shown, the bike wheel would start spinning in the direction shown. It would develop an angular momentum that points up. So just from the relationship that we expect that delta L must equal the torque times delta t, that implies that in order to get the bike wheel ending up with an angular momentum pointing up, we have to be exerting a torque in the upward direction, and that's certainly what we're seeing from our argument here. So I'd be lying if I told you that this stuff was simple. Once you start dealing with cross products and these right-hand rules and torques pointing in different directions from angular momentum and having objects that can rotate around an axis in any direction, things get complicated pretty quickly. Um, this is largely a story for another day. If you were to take Physics 207, you would see a lot more sophisticated discussion of rotations of rigid bodies. But for Physics 107, we're going to call it quits here. So that's it for this episode of What's the Big Idea? Hope to see you again soon. Bye bye.